Salinity gradient is a very interesting technology, and there aren't many examples of it in the world, and we are very, very lucky to have Peter Hague and Geeta Singh present for us today. Peter is a serial entrepreneur. He was the chairman of the Dutch Association of Environmental Technology Companies, and he's got a large number of technical interventions under his belt. And he's the Chief Executive Officer and Chairman of RedStack. Geeta is very accomplished as well, previous projects with SunSource and Hindustan Power, and she runs the Indian energy site, the Indian operation for RedStack. And both Peter and Geeta were very kind to attend our high-level investor forum in KL in February, so we might ask them at the end of it what their thoughts on that were. But I would like to hand over to you both, Peter and Geeta. Congratulations and welcome to this webinar series. Please go ahead.
Thank you. Thank you for giving us the opportunity to present the company and especially the technology with its potentials to you. First, I'll run through the presentation and hopefully later, of course, get feedback on it. Today, we talk about blue energy. What is it and what can it mean for the in the energy mix for the power generation, sustainable energy generation in the Southeast Asia region? That's what we talk about today. What is blue energy? It is generating power, sustainable power, out of contacting two flows of water with different salt concentration. So, for example, when a river, the fresh water, flows into the sea, the salt water, there we can generate power. And the technology used for that is called reverse electro dialysis. It's the reverse of an existing electrodialysis technology, a desalination technology. How does it work? We use membranes. We use two different types of membranes. Membranes to which the salt or the salt water can pass through. One type of membrane is able to pass the positive ions of the salt, the sodium. The other membrane is only able to pass the negative parts of the salt from the salt water to the fresh water. And when we make a pile of these flat membranes alternately, anion and cation plus or minus selective in the pile, and then we flow the fresh water and the seawater and the fresh water and seawater in parallel in between the membranes. What happens then is that the salt wants to move from the salt water to the fresh water. That's a natural process, and in this natural process, a bit of energy is released. And this energy we want to harvest. So when the salt water flows in between the membranes, the positive parts of the salt wants to move to the fresh water to the one direction. The negative parts of the salt wants to move to the other membrane from the salt water to the fresh water. So all positives to the one end, all negatives to the other end, and that's a type of a battery, a continuously recharging battery, a power generator. Per membrane, you only can harvest maybe 50 millivolts. That's not a lot. But when you pile 1,000 membranes in a stack, then you create 50 volts DC. And at the outer ends of the stacks, there are the so-called electrodes, which convert the voltage into current, and then you harvest a DC current. What is the beauty of this blue energy technology? Well, first of all, it is full sustainable. We do not use any chemicals, we do not use any fossil fuel. It's a sustainable solution. It is compact and not high, and it also has a very small ecological impact. I'll come back to that later. But maybe the most important thing is it's full continuous. It's really around the clock. Not only 24/7, but really 365 days a year, full continuous round the clock power generation. As long as the river water flows into the sea, we generate power. So that reduces the need for power storage and power conversion, as you would need by other sustainable energies like solar and wind. One of the beauties, maybe important as well, is that it is DC power, DC current that is generated. It is the ideal power source for hydrogen electrolyzers. Then you do not need conversion, no need to absorb the conversion losses. What is the potential? We are a Dutch company, so first we have take a look at the Netherlands. And then there's two big rivers flow into the sea, the Meuse coming from France, the Rhine coming from Germany, and the Rotterdam area, they flow into the sea. And there is the biggest potential on the in the low waters, the dry seasons, the summertime. Even then, there is sufficient water flowing into the sea to harvest 1,500 megawatt full continuous. And still, there is then sufficient water passing our system that the fish and the ships also can pass. The smaller sites are in the north at the Afsluitdijk, where a branch of the River Rhine is flowing into the sea, and this is where our pilot plant is located. Another one is IJmuiden, the third bullet, 25 megawatt, where a big pumping station is pumping out the low fresh water into the high seawater level to keep the feet of the Dutch guys dry. So we can convert this pumping station, energy consuming pumping station, into a power generating pumping station. I'll talk about that a bit later. And the top one, 3 megawatt, is where, for example, municipal sewage, treated sewage from a big city, flows into the sea. Sewage is also a freshwater flow. When it flows into the sea, there you can harvest power, and maybe use that power for powering the wastewater treatment plant. That's about the Netherlands. What about the world? I must admit, we do not have a detailed overview of each and every river in the world, but some professors from Japan, Turkey, Colombia, they made overviews. And the common conclusion is that the worldwide potential is 1 terawatt, 1 million megawatt all over the place, full continuous, around the clock. And especially the warmer areas in the world are then the most attractive, where around the Ecuador, so India, Philippines, Malaysia, but also Latin America, South Korea, where the climate, where the water is a bit more warm as is in Northern Europe. There the process goes faster, has a higher efficiency. Maybe a few words about the company. Our company is a dedicated company only to work on blue energy. We are a spin-off from the Wetsus Research Institute in the Netherlands. In the meantime, some 18 PhD studies have been finalized on elaborating the concept, the first laboratory test, into something that works, in the laboratory at least. That is what the PhDs did. All this know-how flows into RedStack, including the patents that go with it. The research in the laboratory was done quite a while, but only in 2000. Wait a second, my phone went. So, only in 2005, the company was started, but we had to wait till 2011 that the laboratory showed, yes, it works in the laboratory. And then we thought, okay, time to take it out of the laboratory in the pilot plant, in a real man's world. So we started applying for permits, finance, and so on for the pilot plant in 2012, and we commissioned the pilot plant in 2014. At the end of 2014, our king from the Netherlands, Royal Highness Willem-Alexander, came to do the ribbon cutting ceremony. So we are very honored with this lot of exposure and awards. But then another guy entered our premises, a guy called Mr. Murphy, the guy from Murphy's Law. If something can go wrong, it will go wrong. Well, we have experienced that. Our company, our pilot plant, was the first in the world bringing this technology from the laboratory into the real man's world. So we had to solve many problems to make it work in real life. I come to that a bit later. This is our pilot plant. On the right-hand side, you see the salt water, a branch from the North Sea called the Waddenzee, a very eco-sensitive nature reservoir protected by UNESCO. And the left-hand side, you see the fresh water coming from the River Rhine. And the blue building at the bottom, that is our pilot plant, where the stacks are being developed and tested. Some looks inside the pilot plant. Left and top, you see the outside gray tanks. This is the pre-filtration system to remove the algae and sand and other stuff from the seawater and the fresh water. We don't want that in our membrane stacks, so we must remove it up front. And there are other pictures are inside the pilot plant where we can test, where we do test 8 different stacks at the same time, each fully equipped to have the salt and the freshwater mix and the pressure and the cross flow, counter flow, and so on to do all the development work. There are 2 figures, 2 numbers that please try to remember about the capacity and how much energy can we harvest. The first one is from the water, from a flow of 1 cubic meter per second of fresh water, river water, 1 cubic meter per second, we can harvest 1 megawatt continuous. So as long as the fresh water, the river water flows, we can harvest 1 megawatt. For 100 cubic meter per second, we harvest 100 megawatt, and so on. A normal river, a decent river, easily has more than 1,000 cubic meter per second, so that has significant potentials. The second is how much power can we harvest per square meter of membrane, which is the most costly part of the whole equipment. When we talk about normal river water flowing into a nice salty seawater at a nice temperature, there we can harvest 2 watts per square meter of membrane. That also means that we have to get cost-effective membranes, and that is one of the things we are working on significantly. From all the testing in the pilot plant, it is concluded that the temperature and the concentration of the salt in the seawater are very important for the potential how much energy can we harvest. And this is basic know-how that we use in designing and upscaling to future plants. As said, Mr. Murphy was making a lot of trouble to us during the first years of the pilot plant, and we had to solve many problems to get the membrane stacks running to generate the power. It was easy in the laboratory, and we were facing upscaling issues in the pilot plant. So we worked a lot on the stack design to make sure that the flow of the water goes nice and general, smoothly, equally between all the membranes, using the whole membrane surface in the similar way. We got rid of the so-called spacers in between the membranes, which is the standard for desalination stuff, but that was creating too many problems from clogging, fouling, and scaling. So we changed that, and we deleted this component and made profiles on the membranes, and in that way we solved the clogging and scaling issues. And of course, we also worked on the pre-treatment, how to remove the algae and other sand and stuff to prevent it from coming in the membranes. And we designed operating procedures to make sure that the stack will not get clogged and fouled and so on. It took a lot of effort, but now we can say, yes, it works. Just please don't try to understand it, but this is just as an example of the type of information, the test results we got from the VETSIS PhDs, and our engineers had to convert these graphs and data into operating and design criteria for designing the right stacks and operating the right stacks. For example, this is a picture on CFD modeling. How does the water flow in between the membranes? How is the fusion of the salt? How is the pressure drop in the water? What is the turbulence? And so on. All collected, all proprietary know-how, and this made us available to design the right stacks and operate the stacks in a way that they are stable long-term in operation. As I said, we started from the laboratory, and in the laboratory, a small stack only was used, 0.25 square meter of membrane and a stack. That is just not so much bigger than a liter, a cubic decimeter. That's the same size of stack we started in the pilot plant with, but in the meantime, we did upscaling. We made the stack significantly bigger. We went all the way from a quarter to 500 square meter of membrane in one stack, 2,000 times bigger, that is. And the good news is that thanks to all the efforts, the efficiency is still the same. Per cubic meter of water and per square meter of membrane, we're still harvesting the same amount of power, despite all the upscaling. So we can say there was no efficiency loss in the upscaling. The final step you need to do in the upscaling is going from 500 to 2000 square meters of membrane, only 4 times bigger. The project to do this was approved last month. So we're now ready to start the detailed design and the manufacturing of the bigger stacks, the final size stacks. And this 2000 square meter membrane stack, that will be the building block, the process equipment that will be used in further upscaling into megawatt scale. So once this is done, there's no further technology risk in upscaling. It will just be multiplying into more stacks. How will that look then? On the left-hand top, you see a bit small stack, only 200 square meter of membrane in it. The right top, the blue ones, you see also for certain applications, you can put them in series. But the lower ones, are the pictures are more important. Left, you see a skid-mounted unit. This has 8 modules. This is how it will look. 8 modules on a skid. And that is the building block to build large-scale power plants. And on the right bottom, you see how hundreds of similar modules, identical modules, are connected in a full-scale power plant. What about the ecology? What about environment? Our pilot plant is located at the Afsluitdijk, and the saltwater site, the Waddenzee, is a UNESCO protected area. We have to be very, very careful there not to destroy the flora and the fauna. And also the flow of the final water, the brackish water back into the sea, has to be monitored very well. This has been done by 2 Dutch institutes, Deltares and NIOS, during the last years. More than a year round, they monitored what happens with the algae, what happens with the fish, what happens with the weed, and so on, the mussel eggs in the water. And they also made an extrapolation if a 100 megawatt power plant would be built and operated in this eco-sensitive area. And their conclusion was that even a large-scale application in this ecological, vulnerable and protected environment has no significant, only very minimal ecological impact. So even when we can do it in the ecological sensitive area, well, there's a very important information that in a harbor, in an average river, it will be good to go from environmental point of view. Okay, we are, I would say we're a bit proud of what we have realized so far. We scaled up the technology from the laboratory proof of concept into a TRL 7, a pilot plant operating under real life conditions. But we're not there yet. We have to go further. We have to go upscaling. We have to make the bigger stacks. We have more stacks, but also have to create awareness and create acceptance worldwide to have the technology implemented. And of course, we have to go down the cost curve. We did not yet talk about money. Of course, how expensive will the kilowatt, or low cost will the kilowatt hour prices be that come out of the system. So let's talk about money. Based on the pilot plant, as is operating now in the Netherlands, with a bit of a tactical improvement, but not that shocking, we made a process design for a large-scale power plant, a 100 megawatt power plant. And as a case study, we took the River Po in the city of Venice, emptying into the Adriatic Sea. So the salinity and temperature and so on from that side, we took as input for our process design. And we made a process design for this 100 megawatt power plant. This design we handed over to Dutch consulting engineers Royal Haskoning DHV, and they made an estimate from the investment level, the capex, for this first. It's also important to say the first full-scale 100 megawatt power plant under West European conditions, so the not that low-cost area in the world. This power plant, the first one, would cost about 900 million euro. Please be aware, it's the first one, not yet cost down, and in not a low-cost area in the world. This investment level was then put into the ARENA financial model. ARENA is the European Institute for Renewable Energy Studies, as an agency from the European government. They have a standard financial model with a cost of capital, insurance, everything that goes with a project. We put the data in, and as a result came out that the cost of the power of this first plant would be at about 11 to 12 cents per kilowatt hour. Then later, other institutes other institutes like TNO in the Netherlands, but also consulting engineers, they reported to the government in the Netherlands, the Ministry of Power, what would happen if it really does go down the cost curve. Let's say if 8 or 9 commercial plants are being built, what will happen then? And they concluded, they reported to the government that the cost of energy will go down to 5 euro cents per kilowatt hour. Probably we will need time just after 2040 to realize that. I think that is a very good starting position, very good position in the energy mix. It's certainly more cost effective by that time, the wind at sea in Western Europe. We're also taking a look at the Indian situation, because India, as an example in that area, but other surrounding countries basically counts the same. There are many rivers flowing into the sea, so many opportunities to build similar power plants. There are infrastructural projects being planned in which blue energy power plant can be integrated very well. So to make a flood protection system, to make a pumping station eco-positive, and power generating pumping stations, power generating flood protection systems, and so on. And of course, in most of these countries, the cost of construction of civil works, of mechanical, electrical, are significantly lower as they are in Western Europe. So we expect that the cost down will go faster in this part of the world than would be in Europe. The potential in India, we have to take a global look on that. That's at least 5,000 megawatt full continuous power generations. And I think that's a nice starting point to start working in that part of the world. This is about what I like to share. Thank you for the attention. And I hope to be in contact in the future and get any feedback, questions, follow-up suggestions, and so on. Thank you.
Steve, are you still there? Have you at the end of the presentation?
Yes, I have. Sorry, that was on mute. Thank you very much, Peter. Thanks, Nick. So, Geeta, do you have anything you want to add, or do we want to kick straight into questions?
Now, maybe the most important thing to add, that is I forgot to introduce my colleague director of RedSec India, our branch office in that part of the world, Ms. Geeta Singh. Maybe you can add a few words on who are you?
Good idea.
Thank you, Peter. I think Stephen did introduce me very well. So thank you so much for doing that, Stephen. One thing I wanted to bring into the forefront before we move into the question answer session is that this technology works even more efficiently in the areas with warmer climate. And that is why the focus of this application is more on the Asia and the Southeast Asia part of the world. Compared to, in Netherlands. So this is one of the most important aspect that I thought I would bring out before we move into the question and answer session.
Okay, thanks, Geeta. That was a question I was going to ask. Do we mind if, I think everyone can put their hand up and ask questions, but I've got a few I want to ask off first of all. Peter, the obvious question is, we have a huge problem with waste plastics in the ocean. How difficult is it would you be able to use a component of recycled plastic in your membrane?
There are two answers to that question. Yes, the membranes are manufactured of normal available chemical monomers to make organic membranes. I'm not sure how the recycling would work, but the type of plastic component the monomers are used are not that exclusive. We do not use rare earth metals and these kind of things, so I have a good hope that reused plastic components or sustainable plastic or bioplastics can be used. Second is, we will be pre-treating the river water and also the seawater before it flows into our equipment in our plant. And I think we can use, let's call it a two-step pre-treatment system. First, a pre-treatment system to take all the garbage, the rubbish, the plastics, the plastic bags, whatever is floating around, the coarse stuff. Let's call it anything bigger than a millimeter or so to filter out. And the second step, then we do fine filtration to remove the algae and so on to protect the stacks. But this pre-treatment of both the river and the seawater, of course, removes a lot of plastic and other garbage that otherwise would be floating into the sea. So you could say we help cleaning up the rivers.
Okay, so that then leads on to my next question, because obviously many of our countries have challenges as you described, but they also have problems with red tides and nutrient loads because of excess chemicals. What comes to mind is the problems with red tides and cyanobacteria in Malaysia. Would you be able to combine? Because I'm seeing this as a technology that actually is an entry level, not just about energy, but actually there's a whole bunch of correlated benefits because of it. That's one of the reasons why we got you here. Do you see that there's an opportunity, for instance, to take out nutrients like in Malaysia? Would that be possible?
I'm not so aware, sorry, about the nutrient problem in Malaysia and surrounding countries. I am aware of processes being developed on removing phosphate, for example, ammonium to very low levels to prevent eutrophication. But unfortunately, our system itself does not do that. We can remove solids, so anything floating, suspended solids, which also contain the nutrients, but the soluble nutrients, so the phosphate, ammonium, nitrate, as is in the water, we do nothing on that. It passes through our system. Maybe the positive thing is that once the water is already pre-filtered in our system, in the Blue Energy Power Plant, then it's for the add-on technologies much more easy to remove the phosphate and ammonium from the remaining water flow. So that is the water is then much more conditioned, so there's a better chance of a good efficiency in the follow-up systems.
Because if you look at the work that's done by the Stockholm Environment Institute on the 9 planetary boundaries, one of the boundaries that is profoundly breached is the amount of nitrogen and phosphorus, the disbalance in nitrogen and phosphorus cycles, which is something that we're not really talking much about at the moment, but we will need to in due course, because it feeds into a whole range of other self-fulfilling disaster areas. Okay. I'm happy with this feedback, and I first will bring it also to the Reverse Research Institute in Netherlands, because I know there is a development work going on removing phosphate from surface water flows down to very, very low concentrations. And this is a nice technology. It could be a very nice add-on to such a Blue Energy Power Plant. Yeah, I mean, I know Nick Lambert's going to want to bring up his favourite topic, but this is a great example of co-locating these sorts of activities where you have one technology that then enables another. Nick, I'm not sure if you're going to ask this question, but have we thought about if there's any implications for subsequent use of deep sea water?
Yeah, you've already answered one of my questions, Peter. I thought it was a fab presentation. I love the technology, and it's great to see Geeta again. I've got that idea of co-locating. So one of the things we've learned with OTEC, the OTEC technology, is that the first thing that happens is the environmentalists jump up and down and say, what are the unintended consequences? So it's interesting to hear that you've already addressed that. The second thing we learned about OTEC is it's not actually about power generation. That is a side benefit. It's about the use of deep ocean water for other purposes. So my question was very much along the lines of Steve's. What are the potential benefits of the water after you've generated power with it? So rather than just discharging it, what could be done with it? So I was scribbling down notes while you were talking, thinking, well, could this be combined with a desalination plant? You've already started the process. I think you.
Well,
if I can give it a second, I think you should definitely major on plastic clear up, because I think there are 13 major rivers, which are in India, which discharge the majority or 50% of plastics or something into the ocean. So you should really major on that. Of course, the question is, what do you do with the waste plastic when you've captured it? Is there anything here that could be done alongside nuclear power stations, because they use a huge amount of seawater for cooling? So is there a pre-processing happening in the cooling process for nuclear power stations, which would enable you to then commence your process, so you could have a combined nuclear and or any other power station that uses seawater? I just think you've got a really interesting technology. Sorry, that's quite a long transmission.
Yeah, well, quite many questions. Let me try to answer one by one. The cleaning up of the river, yeah, we can filter out the garbage and plastics and so on floating both in the river water or seawater. It will be coming out as solids, but then it has to be handed over to the waste management company, recycling companies. That is not our key competence. I can't help there, but it certainly will be available as a comparable to separate source collected waste. About using the water, maybe to make it a bit more clear, we will use the water from the river or any other fresh water flowing to the sea, the very last down the line. We are the last one in the users of the fresh water. So we are not competing with agriculture application, with processed water, drinking water. We only will use the river water just a split second, or I should say the split minute, before it flows into the sea anyhow. The water of the river will flow into the sea. We borrow it for half a minute, and then it will continue its flow. I said before, we do filter out the algae and all the sand and all the stuff. So from the not so transparent or not so transparent river water, seawater, we make transparent, clear water, brackish water. That is the outlet. So one option is that we guide the outcome of a system, the brackish water, into the sea and create a clear brackish water zone, continuous brackish water zone, which is another ecological system. And some ecologists would be very happy with that, because it's a beautiful, stable brackish water ecosystem. On the other hand, the sludge that we filter out, the algae, the weeds, the sand, is still alive. We can guide it back into the sea, into the outlet, the brackish water, and then it simply continues as if nothing has happened. We just borrow the water, we borrow the stuff for half a minute, and then it continues its natural flow. So if wanted, we change nothing from the local environment, except for that we harvest power. And especially in our pilot plant in the Netherlands, there the continuous release of brackish water into an existing ecosystem, even especially when it can be made transparent, clear brackish water, is considered to be a huge potential ecological benefit. But that might be different in other places of the world. So there is a choice, a free choice for the ecologists and politicians to decide, do they want a transparent brackish water zone, or do we have the original situation back, except for that we harvested a bit of energy?
And to answer your last question, Nick, where you asked whether our project can be co-located with any other power project. Yeah, so in India, we are trying to do that. We are speaking with some of the large power producers and some of the oil companies who have refineries which are closer to the ocean, or some of the thermal projects which are closer to the ocean. So we're trying to co-locate our project along with it within their facility, so that, we could also save on the infrastructure cost and other ancillary cost. So we're trying to do that. We have not thought of the nuclear power plant at the moment, but that is something that we can absolutely explore.
Yeah, so indeed, indeed, adding on to existing facilities using the same infrastructure, that's indeed a good benefit. Using cooling water, doesn't matter if it's salt water or fresh water, the cooling water as discharge is higher in temperature. And that would be, if you could use that cooling water as input in our system, then the efficiency would even go up. Because as said before, when the temperature is a bit higher, our process works more efficient.
I think that's a really interesting. This is where you'd be well worth having a conversation with Ben Martin in Japan about OTEC, because their biggest challenge is one is a technical challenge, which is building 10-meter diameter pipes 1,000 meters long to suck up the water, and that is an infrastructure cost. So if there was a way of combining your technology with their technology, and you become another beneficiary of deep ocean water, which clearly is salt water as well, maybe there is a combined benefit there, and you share the cost of infrastructure. And one of the solutions they've been looking at is how can that infrastructure be funded by a national government? It becomes part of national infrastructure, and then all the side benefits spin off from it.
Yeah.
Sorry, I shut up for a second.
No, Nick, you've raised a good point, and I probably need to flag that. Just to explain, when you look at various types of financing, and for instance, say you're looking at, and I'll use the example of what ADB did with the Ministry of Mines and Energy in Cambodia, is we helped them develop a solar park, which was copied from the work that was done in Rajasthan a decade earlier. And basically what happened is the government identified a space, they developed the ancillary infrastructure and everything else. So then they turned around to the companies providing the technology, in this case solar. Here is a certain amount of area, here is a connection to a substation, and then they did a reverse auction. Now, if you look at the technology you have, that would be very well suited to a reverse auction. I know that you're probably the only people in the world doing it, but that mentality of developing a park where the technology risk for your technology is borne by you and your investors, but the ancillary costs to government and all these other activities, whether it's deep water or whether it's barrages, is borne by government. What that means is the government can get access to concessional, much lower interest rate financing, which means that there's typically, 2.5 times the difference in the cost of capital between you and the government for something that you might need to develop, which means that it allows you to concentrate on your core business, as you said, that your core competency, but it also allows the end cost for this to be significantly lower and for governments to control it a bit better. That model is, we're looking at trying to apply that in marine areas, and whether it's a marine renewable energy park or a marine special economic zone, with a whole bunch of planning requirements around it. That's the work that we're trying to do with MARES, and we're very close to actually getting a result on that. So that's why your technology is very, very interesting to us, because it fits right into it. And on that note, once the water has gone through your process, can it be used as water for hydrolysis, for electrolysis? Would you do that before or after your process?
If you want to use the water as a source of drinking water, so apply, let's call it normal desalination, or when you want to further upgrade the water to make it suitable for hydrogen electrolyzers, the effluent from our system is brackish water, but the input is, one of the inputs is fresh water. So there is at that site fresh water available, and it would be, I think, a better idea to use this fresh water, the river water, as a source for the desalination or further desalination when needed, or the ultra pure water for the electrolyzers. So that would be, it can be combined in the same facility, because you have the same water pre-treatment system. But I suggest to use the freshwater source and not the brackish effluent as a source for desalination and upgrading.
Okay, thank you for that, because I didn't quite understand the process, and you've now made that pretty clear. So what ends up happening is you have a brackish water outlet.
Yeah, because we are mixing the seawater and the river water. So on average, it becomes a bit of brackish.
Okay, all right. I've run out of questions for you.
Gary has a question, Steve.
Please go ahead.
Peter, Gary, thank you. What a great presentation. Can I just check? I assume I may have missed this in the presentation. The brackish water then gets pumped back into the seawater. That's the first point. And the second one is really just about boundaries. From the photograph you put in your presentation as your backdrop behind you, there's a clear demarcation between the freshwater and the seawater. And is it a prerequisite that it has to be pure and clean? There's no mixing between the two? And if that is the case, are you then constrained and limited by locations where you can put these sites? Because then you also need the physical co-location of the two, and you don't need long distances to pump both the seawater and the freshwater together.
Yeah, thanks for the question. Indeed, we do need both saltwater and freshwater as they are. So seawater, anything 30 grams per liter salt or higher, that's beautiful. The freshwater side preferably is lower than 1 gram per liter of salt. So it might be a touch of salt in it, but it should certainly not be brackish. So yes, we do need both sources separated. In several deltas, that will not be possible. For example, the biggest river on Earth, I think it's the biggest one, the Amazon River. The freshwater upstream in the river, all the way to the saltwater really in the ocean, this gradient is about 300 kilometers. And there is no way that we're going to build a channel of 300 kilometers to bring the freshwater in contact with the saltwater at the sharp line. But in many other deltas, first to start with the pumping stations, to pump out water from the rivers or the lakes into the high level, high tide seawater, or flood protection systems, the same thing. There is a sharp boundary, and there will be more in the future. Or many deltas where there are several branches of the river, not one, but several branches of the river flowing into the sea. And most of these deltas, you will see if you take a good look, one of the branches is pretty fresh water all the way just until it starts to touch the seawater. Other branches, there might be a brackish zone in between. These are not suitable, but the freshwater branches, they are there. We have identified in India at least a couple of ones, and as well in the Netherlands. So this is already incorporated and taken in the input for the worldwide potential of blue energy. Has been taking a look at the various rivers, and it still ends up at being a 1 million megawatt potential.
Right. Thank you for the time.
But indeed, it is a limit. We absolutely cannot use every delta, that's for sure.
Right. Yeah. Thank you.
Are there any other questions?
I would just like to add to your point, Stephen, when you said that, government funding, which can help in, setting up this project. So one of the aspects of this project is that 2/3 of the project cost can be, the equipments required for the 2/3 of the project cost can be sourced locally. So, so given that about 60 to 70% of the project cost can be arranged using local equipments. And if we are to scale this project beyond a megawatt scale, then we can also bring in the manufacturing capabilities of the membranes locally. So that ways, we can set up a project with 100% all local sourced equipments. So this could be another, impetus that can be given to the government to promote blue energy.
Peter, that's a really, really important point. That's such an important point in countries like Indonesia, where local content rules are so important that, and then obviously it makes common sense, right? So effectively, what you're doing is you're doing technology transfer and doing that effectively. Nick, you have a question?
Yeah, I could go on talking about this forever. I've got two questions, please, Peter. One is about the membranes. Do they have to be replaced, and what do you do with them? Can they be recycled, or is there any environmental impact from those? That's one question. And the second is, what happens in some of the countries that we're interested in for mares, so coastal and particularly island states? Does this work in lagoons for example?
Okay, about the plastics, the building brick of the plastics are relatively simple chemical organic monomers, not so special. The know-how is in how to mix, how to combine these monomers and how to cure them to make a good membrane. But the organic building bricks are not that complicated, and they absolutely are harmless, and they're not containing rare earth metals or something rare as that. That also creates a possibility that there will be low cost when we go really down the cost curve, which is needed. The membranes will have at least, that's what we are using now in our design, a 7.5-year lifetime, and then would have to be replaced. But down the cost curve, and is also supported by statements from the membrane manufacturer, they say 15 years certainly will be possible. Once we got the good stuff up and running, the cost down curve will implement 15 years lifetime for the membranes. Then they have to be replaced, and they can be treated as normal but pure plastic waste in plastic processing equipment. And how that will be, I don't know. I'm not a specialist in that, but it is normal plastic waste without toxic components. Decentralized applications on islands, for example. Yes, if there is a freshwater source flowing into the sea, then we have a nice opportunity. That can be a small river, but it can also be the effluent of a wastewater treatment plant, which is also a freshwater source. If you would look at such plants, they probably are only very small, maybe just a few megawatt. And as today's level of cost, it will be too expensive, as we are not yet down the cost curve of the membrane modules. But once you have set up 1 or 2 or 3 100 megawatt power plants, are manufacturing many membrane modules, then we are down the cost curve. And then we pick these lower cost membrane modules and use them in the small scale, few megawatt applications. Probably at these idle locations, the cost of power is a bit higher than 6 or 7 cents per kilowatt hour. So I hope within a few years this will be a cost-effective application for these islands and remote areas.
Yeah, I think this is where the... Sorry, Geeta, beg your pardon.
Sorry, just to add to that, the plant is designed for 30 years. Only the membranes will have to be replaced every 15 years. So I thought that's an important point to mention.
Yeah. And that is also put in this arena model, the results as the financial, the 11 cents per kilo, as we talked about already.
Yeah, I think this is where combining technologies is really interesting. And I know that you'll be focused very hard on, we need to get this from TRL 7 to 9, we need to scale it, we need to get the costs down and so on. And that, of course, is one of the problems with the renewable energy scene, is that you get pockets of people doing different technologies, and it's how do you get them to think together? And because, of course, they don't necessarily have the resource to do it. But I think you've got a really interesting opportunity to influence that wider debate. Combining you with floating solar and wind, for example, and a desalination plant so that you get the fresh water. I mean, it all sort of starts to fit together, doesn't it? Although it becomes a complex infrastructure, and then the various agencies that you're trying to persuade to work together are all saying, well, I'm not a wind farm operator, I don't do OTEC, I don't do this, I don't do that, and therefore I don't want that risk. It's how do we absorb that risk or mitigate that risk? I'd be very pleased to introduce you to Benjamin Martin if you didn't meet him, Peter, because I really do think a combined conversation about OTEC and your technology would be really interesting, and I happily make that happen. The other introduction I made for him, and we've had some conversations around it, is a very interesting technology in University of Edinburgh, which is marine biosensors, and these are living cells connected. I don't know how it works, but they're glued to a chip, and the electrical power flows through them, and they tell you if there's ammonia in the water or whatever particular characteristic that you're concerned about. And I'd love to talk to you offline about that and the I've forgotten the name of the agency that has been monitoring the environment that you're working in. I'd love to talk to you about that as well. I just think you've got an opportunity to be very influential beyond your specific remit. So I think you can say, if I'm going to capture X tons of plastic a year from a millimeter above, and I'm going to stop it going into the ocean, what happens to that plastic? And I know you're not a waste disposal expert, but you can be very influential about what happens to that. And take it back to Geeta's point about the in-country resource that is building infrastructure and so on. I think there's a really, really interesting conversation to be had there. And I think you should major on it because whilst we've got that other wonderful Dutch lad that's out there gathering plastic in the Pacific, the answer to plastic in the ocean is to stop it getting in there in the first place. Sorry, I could go on about this, but I just think you've got such an interesting approach and an opportunity to be very influential.
Thank you for these comments and suggestions. We certainly will pick it up and elaborate on that. Thank you.
So I'm going to change tack a little bit. I know we've got 9 minutes to go, and if anybody wants to jump in with a question, please do now, or I'm going to ask a slightly different question and challenge Peter a little bit. Has anybody else got another question? Okay. So, Peter, Mr. Murphy is increasingly being seen all around the world in all sorts of circumstances, and it is his wife, Mrs. Murphy, and the kids as well. So, you know, Holland obviously has an issue with sea level rise and has a fairly well-developed strategy for fighting and mitigating and then abandoning areas that will rise because of sea level. Just out of interest, is there an implication for this technology being used in conjunction with some of those measures? For instance, you might have an area, you may be able to make use of infrastructure to, like a barrage. Have you thought about that component? Because that's something that's going to increasingly become an issue.
Yeah, if you would have to build this flood protection system in any delta, it still would mean that the river water has to go out in the sea. So you will need some type of sluices that you will open up only when the outside water is at low tide, or you will have to implement pumping stations to lift the low river water against the high seawater level. And this is basically the same thing as an existing pumping station. In our plants, we are pumping the water anyhow. Basically, I didn't mention it yet, but once we have a 100 megawatt power plant operating, from this 100 megawatt, we will need 25 megawatt to pump the freshwater, saltwater through the pre-treatment, through the membrane stacks, and let it flow as brackish water and the outlet again, assuming that the inlet, the freshwater, and the outlet and the seawater is at the same level. Then we consume 25% of our own generated energy. But once the seawater level is higher and we have to lift the river water up into the seawater as a pumping station against the high tide, we need a bit more energy. Maybe we need 5 or 10% extra of the generated energy. That means that still 60-65% of the power is net available to put back into the grid or for whatever use. So then when you integrate that in the flood protection system, instead of putting in a power consuming pumping station, you put in a power generating blue energy plant. So the whole flood protection system will be power generating. So it has it would even have a bit more positive eco footprint of how you want to call it.
That's outstanding, because one of the challenges we have at the moment is, and I know this isn't related to energy and this isn't related to, it's partially related to environment, but looking at solutions which are cross-sectoral and asymmetric is something that development banks don't do particularly well. Have you got anywhere in the region where you might be able to test bed that?
Yes, for example, we are at the Afsluitdijk, which is a flood protection system. Another thing is that together with Korean power company KEPCO, we are doing a case study, selecting a site selection, which of 3 sites would be most suitable to set up a large-scale plant. One of these sites is indeed an existing pumping station to pump the low water against fresh water against the high-level salt water. The second one is a relatively new build type of flood protection similar to the afsluitdijk, where the river flows into the lake and then into the sea, and there has to be created an outlet. Well, that's a nice opportunity as well.
Yeah, and it's 24/7. That's the beauty of it.
Yep, absolutely.
Oh, wow. I didn't see that coming. That's not common that I get surprised, Peter. Thank you very much for that.
Yeah.
That is a discussion in itself. Just out of interest, when do you reckon you might be able to talk more about that existing pumping station and present some more information about that?
Well, I want to be in Korea and China next month. I will be there, I should say, and I hope that we sign then this and release, kick off this feasibility study. But the site I can share with you. I do not know from the top of my head, but I have it somewhere in my file what the name of that site is. I will forward it to you separately.
So Korea is obviously a great supporter of the Asian Development Bank, and we know everyone. We know the folks from KEPCO and the various ministries in Korea. If we can demonstrate that if we can get a demonstration of that project, I can tell you there will be a lot of people in Jakarta and in other parts of, I mean, obviously in India as well and Bangladesh. This will have a significant implication. So, Nick, I'm thinking Bangladesh for protection measures. Yeah, that would
absolutely.
be. Yeah,
absolutely.
That would be.
Yeah,
No offense.
I agree.
Gita, I want to know. I'm sure there's lots to do in India as well, in Odisha and some of the other states as well.
As long as we don't talk about hockey, we can very well cooperate with the Bangladesh and surrounding countries.
Yeah, we'll just talk about cricket.
Oh, sorry. Doesn't make it any better.
No, not really. So, on that very important note, look, what a great session. What a really, really interesting session. It was interesting because we've only had about 10 or 12 people on this session, but hopefully this gets a significant amount of recovery, because I think that there's a lot of moving parts to this, and it's not just the MARES component, which is the ocean-related energy, the marine, onshore, offshore interactions, but there's also this area of coastal protection, which, wow, be really interesting to see how that goes. So, Peter and Gita, thank you so much for your time. And as I said, thank you for coming to the High Level Investor Forum. It was a great pleasure to meet you both there. And it's been a great pleasure to have you present. And Nick, if there's anything you want to say before we sign off?
No, I've fallen in love with another technology.
Do you know, it's very interesting. One of the first villages that's going to go underwater with sea level rise is actually in the UK. There's a very low level village that they've evacuated already. They know it's going to go. I can't remember where it is. I think it's in Wales somewhere, Nick.
Yeah, there's lots of coastal erosion going on around us. I think there's you got me thinking the Thames Barrier. There's all sorts of things here. The problem will be the sharing the understanding across the different technologies and getting the integrators to combine them. That's going to be the problem.
Yeah.
There's some very I referred to the Project Orion in the Shetland Islands in my presentation in Kuala Lumpur, where they're going to be using renewable energy to power the extant oil and gas infrastructure for the next 20 or 30 years. So you can just see, right, well, how does your technology fit into that? So do you use renewable energy to create to do osmosis, to create fresh water, to enable you to use power? And in that process, are you just moving wooden dollars around, or are you actually gaining power generation benefit? And they also plan to run electrolysis plants to make hydrogen. So does yours, and they're surrounded by salt water. They don't have large rivers, but they probably have reservoirs and so on. They have fields and things. So who knows? It's just really interesting technology. So Peter, you're going to have to become an expert beyond red stack.
Now there are several spin-off opportunities there, that's for sure, and we'll pick up the good ones.
Yeah, I think definitely looking at the OTEC plant in Kamishima in Japan is worthwhile, because when you look at the array of small industries that are blossoming behind that deep ocean water feed, then you really do see the potential.
Yeah, there's things that people think about over and above what all of us in this call are thinking about. For instance, in Kagoshima, one of the things they make is shampoo. They make beauty products from them. Yeah,
you need some of that, Peter. Lots of shampoo up there.
Yeah, you're dismissed.
I think it's time to go. Say goodbye.
Okay, so on that note, everybody, thank you very much, and we'll see you for the next session. But great job, and looking forward to seeing RedStack power the world. So great job.
Thank you for the opportunity, and look forward to further cooperation. Thank you very much.
Thank you so much.
Thank
Bye-bye.
you. Thank you again.